Gauge theories and Hilbert theories.
So, thank you very much for the introduction, and I would like to thank the organizers for the opportunities to speak here, and also for placing my talk after Nakajima's talk. This is very convenient for me, because I will tell you somehow the physics side of the story, which is behind this monopole formula, which was mentioned in the very first slide of the talk. And so this is based on a series of papers, initially on three-dimensional n = 4 supersymmetric field theories with Anani and Zaffaroni, then Meccaria and Ferlito. And more recently, we've been trying to generalize the same kind of physics argument to theories with a lower amount of supersymmetry, say three-dimensional n = 3 and n = 2 field theories. So let me start by reminding you that the natural way in which geometry appears in supersymmetric gauge theories, as we heard also before, it's in the study of moduli spaces of supersymmetric vacua. So let me consider four-dimensional n = 1 gauge theory, so with 4 supercharges. Its data is defined by a compact gauge group, G, to which we associate vector multiplets, representation R, which is typically reducible. This describes the matter fields in the theory. These are chiral multiplets, which crucially are complex. And the G-invariant polynomial W of X, holomorphic in the chiral multiplets. This is the superpotential. And then, given this data, we can write down the scalar potential of the theory, which is essentially a sum of squares. So first, we have the squares of the F terms, the derivatives of the superpotentials. And then from the vector multiplet sectors, we have the squares of the D terms, which are moment maps of the action of the G group on the matter fields. And if there is a U1 gauge group, this moment map can be shifted by so-called Fayet-Iliopoulos parameters. And we're interested in studying the moduli space of supersymmetric vacua, which is the set of zero energy field configurations, which set to 0 the scalar potential. And so we want to find the field configuration for the complex fields in the chiral multiplets, which sets to 0 these F terms and D terms, and mod out by the gauge group. So this is a symplectic Kähler quotient. But alternatively, we can describe it as a holomorphic quotient by the complexified gauge group of the space of solution of the F terms equations. So more generally, even if you don't have a gauge theory, four-dimensional n = 1 supersymmetry implies that this moduli space is scalar, but we won't use the Kähler metric today. We will view M rather as a complex algebraic variety, and in particular, we'll be interested in the ring of holomorphic functions. So this leads us to considering gauge invariant chiral operators, which are annihilated by half of the supercharges, odd generators of the Poincare superalgebra. And so we're interested in these chiral operators because their expectation values are holomorphic functions on this moduli space of vacua. So two important facts about them is that we can essentially work at the level of the cohomology of this Q-bar supercharge because the expectation value of Q-bar exact operators vanishes. And as a consequence of this, the correlation functions of chiral operators actually do not depend on the insertion points and factorize. So still we're interested in the product of gauge invariant chiral operators. So in this chiral ring, where now these structure constants are really constants. And as was mentioned in the previous talk, this relates to the coordinate ring of the moduli space, and we're interested in questions such as determining the generators of this ring and the relations. So in the context of four-dimensional n = 1 gauge theories, these gauge invariant chiral operators are gauge invariant polynomials in the matter fields X. So a convenient tool to study gauge invariant chiral operators is Hilbert series, which is a generating function that counts all chiral operators with a grading provided by the R symmetry R. So this it's a charge which does not commute with supersymmetries. And if there are other global symmetries, say flavor symmetries, which commute with the supercharges, we also weight these gauge invariant operators by these flavor charges. So just to give some simple examples to explain what I'm doing, so let's consider a case where the gauge group is trivial, and so we only have to impose the F-term equation. So say if you have a single chiral matter field X with no superpotential, then the moduli space is the complex plane, and the Hilbert series just counts powers of this chiral multiplet, and so we get a geometric series. If instead there is a superpotential, say x to the n plus 1, which sets by the F term x to the n to 0, then the geometric series is truncated. Another example which might reappear later is the so-called XYZ model, where we have three fields x, y, z subject to this superpotential, which sets to 0 by the F terms the product of any two of the fields. And so the moduli space consists actually of three branches parameterized by expectation value of only one of the three fields, x, y, and z. And similarly, you can compute the Hilbert series just say using, for instance, this structure, and it takes a more complicated form. So in the context of a supersymmetric gauge theory, say if you have a gauge group G, what you do to compute the Hilbert series is to start with the Hilbert series, say, of the ungauged theories, where we only impose the F terms, and then we integrate or average over the gauge group with a Haar measure. So for instance, consider a gauge group G with one field, chiral field phi in the adjoint representation. This will be useful later. And then, so we are counting gauge invariants of the adjoint representations, and these are well known to be just products of Casimir invariants. So another example is, say, consider U1 gauge theory with two flavors. So it's given by these squeezers. And we can compute, again, the Hilbert series and count gauge invariance. In this case, because we have U1 gauge group, similar to here, we could shift the D term by this phi Heliopoulos parameter. And now, on the Hilbert series side, we can actually insert this power x to the minus b. So we, instead of counting gauge invariant operators, we can count operators of charge b. So these are, and for those of you who are familiar with gauge inert sigma model toric description of the conifold, this is just what we are computing. So when b is 0, you can compute this Hilbert series and obtain the algebraic description of the conifold. So there are 4 generators subject to one relation. And instead, when b is non-zero, we're counting a holomorphic section of a line bundle, which are given by monomials in the matter fields of charge b. So this corresponds to the two resolutions of the conifold related by Floch transistor. So in what I've described so far, in the context of moduli space of vacua for dimensional n equal 1 supersymmetric gauge theories and Hilbert series, so mathematically what we found for the moduli space is that these are Kähler quotients, and if we consider Higgs branches of four-dimensional n equal 2 theories, we would have found hyper-Kähler quotients. And on the physics side, the analysis was mostly classical. I mean, of course, there have been many fundamental works in the 90s, notably by Seiberg, which were about studying quantum corrections to these pictures. But from our point of view, this, say, will lead either to lifting the moduli space and breaking supersymmetry, or to complex structure deformations, to which the Hilbert series is not sensitive. So in the rest of my talk, instead, I would like to discuss a different construction that, say, mathematically yields Kähler or hyper-Kähler moduli spaces, and physically is inherently quantum. And this is based on the physics of three-dimensional supersymmetric gauge theories, say, with supersymmetry at least n equals 2, which can be obtained by, say, dimensional reduction of n equal 1 in 4 dimensions. So this type of theories have been studied a lot in the literature in the 90s, and particularly also the moduli spaces of vacua. So today, I'm going to try and take a slightly alternative, though not completely unrelated point of view. So we'll be counting gauge invariant chiral operators in these theories. So, and So the main difference between three-dimensional supersymmetric gauge theories and four-dimensional supersymmetric gauge theories, at least as far as I'm concerned today, is in the presence of 't Hooft monopole operators in 3 dimensions. These are new local chiral operators that exist in 3 dimensions, and the important thing is that they are subject to quantum relations, which, however, do not descend from a superpotential. So the challenge is to understand these 't Hooft monopole operators and, if possible, derive these quantum relations. So what are these 't Hooft monopole operators? So let me quote here the opening of a paper by Kapustin in, I think, 2005, which goes something like this. It is known to quantum field theory aficionados, but not appreciated widely enough, that local operators need not be defined as local functions of the fields which are used to write down the Lagrangian. So I think now, more than 10 years later, it is much more appreciated. And so how can we define local operators otherwise? You can define them by imposing a singular boundary condition in the Euclidean path integral. And these are local operators if the singular boundary condition is at a point. So in particular, in the context of these 't Hooft monopole operators, the boundary condition that you're imposing on the Euclidean path integral is that the gauge fields have a Dirac monopole singularity at the insertion point x. So say this is defined by an embedding of U1 into the gauge group. Say we have an insertion point x, a 2-sphere around it, and there is a Dirac monopole singularity for the gauge field. So if you want to preserve n equal to supersymmetry, this requires to turn on to impose a singularity also for a real scalar sigma in the vector multiplet, which is related to the singularity for the gauge field by supersymmetry. So even though the definition of this 't Hooft monopole operator only uses fields in the vector multiplet, one can check that this singular boundary condition define a chiral multiplet, so it preserves the supersymmetry of a chiral multiplet. So we are going to replace vector multiplets by chiral multiplets labeled by M, the magnetic charge, which can take to be a constant element of the Cartan subalgebra of the Lie algebra of the gauge group, modulo residual Weil gauge transformations. And if you impose a Dirac quantization, then the magnetic charge is actually an element of the weight lattice of the Langlands dual group, again, modulo Weil transformations. So I explained this definition of 't Hooft monopole operator for the gauge field, the dynamical gauge field of the vector multiplets, but you can actually play the same game for any global non-R symmetry and introduce some background magnetic charges. So more generally, we'll label monopole operators by the dynamical magnetic charge M for the gauge symmetry, background magnetic charge M hat for the flavor symmetry, and the background charge B for the topological symmetry, which I'll introduce in a second. So as I said, these monopole operators are actually chiral multiplets, so we need to count them. They're on the same footing as the other chiral fields in the theories. In particular, we have to count them in the Hilbert series. And so we need to know what their charges are. So first of all, there is this topological symmetry, which has also appeared in Nakajima's talk. So there is a topological symmetry group, which is given by the center of the Langlands dual group, under which monopole operators are charged. So in particular, if the gauge group is UN, or say the complexification is GLN, there is a U1 symmetry under which monopole operators are charged. So more generally, in three-dimensional theories, you can have gauge invariant, say, Chern-Simons interactions of this type, where, say, A sub B is a gauge connection for, say, some U1 gauge symmetry in the theory. And for us, this could be a dynamical gauge symmetry or a background gauge symmetry for the global symmetries in the theories. And then when introduced monopole operators, so we have a magnetic flux here this induces an electric charge for the monopole operator just by the Chern-Simons coupling. And so at the classical level, we have a formula for the charges of monopole operators of this type involving the Chern-Simons levels. But this is not all. So there are, due to the spectral asymmetry of the Dirac operator in the monopole background, there are actually quantum corrections to the charges, which are given by this formula. So essentially, we have a sum over all fermions in the theories, the charge of the fermions times the absolute value of this linear combination, which I call, for physical reason, the effective mass. So given a gauge theory and the matter content, you can compute these quantum corrections to the charges of monopole operators. And so we will count in our Hilbert series monopole operators according to their classical plus quantum charges, which are given by this expression in terms of an effective Chern-Simons level that contains a classical plus quantum correction. So, so far in describing and introducing these monopole operators, we only use fields in the vector multiples, and these are, for a reason that will become clear in a second, I call these bare monopole operators. So we can do it for the gauge, flavor, and topological symmetry. But let's consider the gauge group. So we start with the gauge group G, then we introduce this monopole operator, and this breaks G to some residual gauge group, G sub m, which is the stabilizer of the magnetic charge. But in addition, if you study the BPS equations by supersymmetry, you can see that you can actually dress this bare monopole operator defined in terms of the fields in the vector multiplet by matter fields, so chiral multiplets, which are massless in this monopole background. So they satisfy this condition that their effective mass is 0. And these are what I call residual matter fields. So these are moduli of the monopole, of the BPS monopole configuration that we can turn on at 0 energy cost. So what we're going to do is to dress a bare monopole operator by gauge invariants of the residual gauge group, which are constructed out of these residual matter fields, and then average over the Weil group to have a full gauge invariant. So when we look at the contributions, say, to the Hilbert series of this of the gauge group and the matter fields, we have formulas of this type. So, so if you consider, say, the massless gauge fields, which belong to the residual gauge group of the massless matter fields, what I call the residual matter fields, they contribute to the Hilbert series in the same way as I introduced for four-dimensional n=1 theories. But those which are massive in the monopole background, they contribute these prefactors, which take into account the quantum corrections to the monopole charges. So these are the type of contributions to the Hilbert series. So to summarize, the dressing of monopole operators is governed by some residual gauge theory, which is labeled by the dynamical and background magnetic charges. So it has some residual gauge group and the residual flavor group. It has some residual matter fields in the representation of this residual gauge and flavor group. It might have some residual superpotential, which is obtained by setting to 0 massive fields. And more crucially, it has some background electric charges, which is the charge carried by the monopole operator. And so much like say we computed in this slide, we can compute, say, the Hilbert series for this residual gauge theory, which I will call dressing factor for a reason that will become clear, in a second. So now we have all the ingredients to understand this monopole formula for the Hilbert series. So the Hilbert series that we define in the presence of background magnetic charges will count all chiral gauge invariant operators according to their topological R charge and flavor charges. And we're counting gauge invariant operators of fixed magnetic charges under the global symmetries. So we do that by summing over all monopole operators magnetic charge M under the gauge symmetry. So we have say, a prefactor here which carries takes into account the charges of the bare monopole operator. And finally, you can dress the monopole operator by this gauge invariance of the residual gauge field. So we have the Hilbert series of this residual gauge theory that provides this dressing factor. And so this is a general formula which applies also to three-dimensional n equal 2 theories. I will give some examples in a second. So one comment here is that the magnetic charge lattice, say for n equal 4 theories, is really the weight lattice of the dual group modeled out by the Weil symmetry. But for lower supersymmetry, then there can be non-perturbative effects, and as a result, this lattice that we have to sum over is a sublattice that can be computed by using physical considerations. So let me just apply this method to this reasoning to three-dimensional n equal 4 gauge theories, in particular the Coulomb branch. So we have now a gauge group with the n equal 4 vector multiplets and a representation for n equal 4 hypermultiplets. We fix, say, n equal 2 subalgebra or an n equal 2 complex structures, and we can apply the previous reasoning. In particular, we're interested in the Coulomb branch, which is the branch of the moduli space where the hypermultiplets do not take expectation values. So we can apply the previous formula for the charges of the monopole operators, and essentially the only crucial one is that the R charge of a monopole operator is given by this expression. There is a negative contribution from the gauge group or vector multiplet and a positive contribution from the matter field's hypermultiplets. And so the Hilbert series of the Coulomb branch can be computed by summing over all magnetic charges. There is a contribution from the topological charge and R charge of monopole operators, and then we have a dressing factor. So in this case, on the Coulomb branch side, we're setting to 0 all hypermultiplets, and so we only have to dress monopole operators by powers of phi. And so this dressing factor is simply the Hilbert series that counts Casimirs of the residual gauge group. So let me make a few remarks here. So this definition includes, in this definition, we can include for free some background charge, magnetic charge for the flavor symmetry. When you set it to 0, you get actually the Hilbert series of the Coulomb branch as a cone. But it's also interesting to turn on this background magnetic charges to look at partial resolutions and line bundles. So I should also say that it was realized later by Razamati and Willett, and more recently also by Closet and Kim, that this Hilbert series, which only counts gauge invariant chiral operators, can be actually obtained as a limit of supersymmetric indices. In this limit, essentially, the fermions do not contribute to the index. But I would like to stress that this is a very computable limit, and in particular, you can use this formula to often deduce charges of generators and relations, and sometimes to determine completely the chiral ring. So I should also mention that now there is a more direct way of computing the chiral ring relations that due to Bullimore, Di Motta, and Gaiotto that we might hear more about today. And but still, I would like to stress that this formula is still useful, maybe to be used in conjunction with this construction. And in particular, it applies regardless of the Coulomb branch being a complete intersection or not. So it's very general. So let me just briefly give maybe just a couple of examples, say for 3D n equal 4 theories. So you can consider U1 theory with n fundamental flavors. Then you have a single sum over magnetic sectors. You sum it up, and you find precisely the Hilbert series of C2 mod Zn, which is the Coulomb branch as was proposed by Intriligator and Seiberg. And from the Hilbert series, you can actually see isolated 3 generators and the relation of the Coulomb branch. And similarly, say for higher rank case, So for UK gauge group, the sum is more complicated, but still you can find that there are, say, 3K generators subject to K relations, and recently the explicit form of the relations were found by Bullimore et al. And also an interesting application of these methods is to the study of instanton moduli spaces, which can be realized as Coulomb branches of three-dimensional n = 4 gauge theories. And with some, say, mild conjectural modification, you can actually find formulas which are valid for any gauge group, unlike in the ADHN construction. So since I'm running out of time, let me just flash quickly one example with n = 2 supersymmetry. So we have, so this is the formula that follows from the previous consideration for a three-dimensional n = 2 theory, and are setting the background magnetic charges to 0 for simplicity. And so, and as I said, an interesting difference in the context of three-dimensional n = 2 theories that are quantum effects, say in particular instanton corrections that lift part of the Coulomb branch. And this can be implemented in the Hilbert series by summing over sublattice that can be determined just by physical considerations. So in particular, say, if you consider UN theory with NF fundamental flavors, then the sublattice is actually only two-dimensional rather than n-dimensional, as it would be in the n = 4 case. But you can compute, say, the Hilbert series using this formula. And what I want to stress here is that essentially just by looking at the structure of this quantum sublattice and the residual gauge theories in the various cases, say in the interior of the sublattice or at the boundaries, this information is enough to completely determine, so at least in this class, the chiral ring. So this type of relations were obtained in the 90s by assuming some dynamically generated superpotential, which is singular. So I would like to stress here that here I'm not using this superpotential at all. I'm obtaining the same relations by this kind of analysis. So let me skip the next example and jump to the conclusions. So what I presented today is some general framework to count gauge invariant chiral operators that parameterize moduli space of vacuum of three-dimensional n = 2 and higher gauge theories. And so I hope I convinced you that this kind of techniques can simplify the study of the chiral ring. And in favorable cases, we can determine the chiral ring and the moduli space of vacua completely. So there are some open problems that would be nice to address and that were addressed in the n = 4 case. So here, as I said, in favorable cases, we can actually determine the chiral ring, but not in general. So it would be nice to have a construction to derive explicitly chiral ring relations, similarly to what was found by Bullimore et al. In the n = 4 case. So we also heard about the mathematical definition of the Coulomb branch of 3D n = 4 theories earlier in the talk by Nakajima. So it would be also nice to have a mathematical definition of this moduli space of 3D n = 2 theories. And finally, it would also be interesting to find some kind of path integral derivation of this Hilbert series as an index, at least in the case where the moduli space of solution of F terms is a complete intersection. So with this, I stop. Thank you for your attention.
Questions? Well, I guess everybody is looking forward to coffee. All right, with that, let's thank the speaker again.